We continue on the frequency domain. This section is the
I'll be looking at it. I'll be fine. At least for this class. When we get to the vibrations, I'll probably take it.
So here let us use this as one example. And so basically for any kinds of the feedback loop systems, and we can always write the transfer functions. So simply we use M defined as the transfer functions. And here we want to know basically is from our introductions last time, we know the magnitude and phase angle of this transfer function basically can be related to the output.
Isn't that just G over 1 plus GH?
Yeah, I think so. Yes, thank you. Okay, so now for this one, basically here we the typical gain and phase diagrams for M of S will be just like this. This is the magnitude of the M. And in terms of the omega, and usually here we put it in the log scale. And the same thing for the phase. For this one, M schematically we have this curve. And then here, if, for example, this is the original magnitude, and say, for example, whatever the magnitude, say, define the original here, say, equal to 1, then if we scale to 1, then here is 1 over square 2. This corresponding is called the omega R, omega bandwidth GW. Okay, so this one denoting is the bandwidth here. And for the phase, most of the time for stable system, their phase is most of the time is negative phase lag. So basically here we're starting from 0. They usually withdraw it go to the negative range. Again, and why we want to know the gain and phase, and the reason we can see the lectures last time. Okay, basically here is the kind of the convolution concept. Basically, of the output will be equal to gain of the system, phase of the system, and then in algebraic way composite to the input. Okay, so here that is the reason we're doing this. And so for those things, and we usually try to show graphically. And again, the first most important parameter is we want to know the bandwidth. the bandwidth basically give us the kind of the range we know the system's amplification basically will be sufficiently large. And say if the system's gain is falling into the bandwidth outside the bandwidth, then we can recognize the system magnitude will become smaller. That means the magnitude of output will be small and become insignificant. And that is the range of the operation we want to avoid. Okay, sometimes we want to control the output to a certain, say, magnitude. Then in addition, hopefully we can select the operation, the frequency, that means within the bandwidth. That's the first one. The second one is this one. This is from here, the magnitude here, and it's called the MR, and that means basically is the peak of the gain of the system. Okay, so that means that is the maximum gain you can, or the maximum amplification you can reach given the system, given the input. That is the maximum output, the magnitude of output you can expect. Okay, and from this curve we can also have other discussion regarding the stability. And so that means certain systems have a certain features, and from this graph later on, if we really have time, we can get into that directions. But anyhow, the two plots together, we have the phase, and we have a magnet, we have a gain with a phase. This one basically we say that is called the Bode plot. Bode plot of the transfer functions, or Bode plot of the system, basically indicating is composed of two portions. One is the magnitude, one is phase angle. We draw the magnitude and phase angle in terms of the log scale of the frequency. The two together is we call the Bode plot. And maybe here I can give you introductions in using MATLAB, how to use Bode plot. And basically MATLAB is using this command, okay? And how to use this one, probably we can do an example here. Say, for example, if we consider a transfer functions and is s plus 2, okay, that is a very simple system. And then here we can write it out is this. We simply, let me do the backward. So here we have a system, and we have the omega, the scale, the range we want to plot. And what is the system? And system basically is the transfer functions, TF, of this system. So the numerator equal to 1, and denominator equal to 1 and 2. And what is omega? Omega is the range you want to define, and usually in the plotting you should give yourself a certain finite range of the plotting. So for example, here we can say omega, and here is the in log scale, so here we put into log space. Okay, and that is the MATLAB command to draw the log scale. And say, for example, here you want to draw is say from -2 to 2. So basically you're asking drawing is, here is a command. You draw is the omega is in the range 0.01 to 100. Okay, simply you draw your domain of the plot is from 0.01 to 100, and then this one you can adjust by yourself. And again, this one is how we take in the log scale. I think that pretty much. So from here you should be able to see certain Bode plots of a system, and then you can free to adjust this range to say, for example, to help yourself to identify the bandwidth, or to help yourself to estimate the peak of the M. So today we simply practice how to how to manually draw the Bode plot of common functions. And then for the complicated form of the transfer function, and then probably you can use MATLAB. Okay, most of the time using manually draw it, and that will help you to design the controllers, and we will talk about today. So today we, I think they have used certain chemical to clean the board, and I don't know why but I have a hard time to have the mark, have the ink onto the whiteboard. This is a new one, and I tested it in my office, and it's good, but not good here. Okay, so here let us to practice and how to draw the Bode plot exactly for simple transfer functions. And here Bode plot is log recently plots of g of m j omega, okay, of a transfer function. Actually, Bode plot can be applied to any functions, but here for these chapters, the overall goal is to study the behavior of the system. So here I pick up is the transfer function, but actually this can be applied to any function of the function of S. So, and I believe most of the textbook, and for example, in our textbook, they're using the symbol G. Okay, and rather than M. And so most of the textbook, they simply say the Bode plot of function G. And that one sometimes, if for people that you involve too much, you might be confused about that G with this G. It's no. Okay, so basically here I want to make that clear. The Bode plot can be applied to any functions, okay? So say Bode plot of the open loop system, the Bode plot of the controller, or Bode plot of the transfer function, etc. Okay, so here let me just focus on this one. So basically Bode plots composed of the two plots here and log 10 omega, and usually we place the magnitude onto the top here, and usually we put the phase at the bottom. Okay, and that is the common exercise. And this is m of the j omega. And most of the time we just drop the j. We simply write it out in terms of the m omega. Okay. So this is the log scale. Furthermore, I not only we take a log scale in the horizontal axis, we also people like to in the practice like to take a log scale in the vertical axis of the magnitude as well. And the major reason, I guess, okay, and I don't have the direct evidence, but that's my guess, is the magnitude, the variation of the magnitude of a system, typical system, is large. Okay, so here we like to take the log scale as well. So here is we take the log scale of the 10 on the 10 base, and then we multiply with 20. Okay, we basically here is we multiply 20 with the log scale of the n.
Why?
And here basically, let me give you the reason why I'm expecting this question. Given a constant, let me define why we want to take that spatial scale. Given a constant k, then if we take the 20 log 10 of k, and this spatial scaling will have the unit we call the dB, decibel. And decibel is a very common unit for power, in particular for decibel, for
Sound vibrations?
yeah, so for, how to say?
Like sound vibrations?
Yes, sound, yes, okay. So basically here, we like to adopt that one, and the people basically here using taking up the spatial unit here. Okay, so here in terms of Bode plot, in terms of the magnitude, we commonly we like to use decibel as the unit, as a measurement. And again, the one I guess is due to the variation of the magnitude over omega is large, so I like to put into the scale, log scale. Okay. So that means 1 dB, the dB from the decibel, DECIBLE, okay? So basically you can see the decibel unit, basically that takes, say, for example, we can calculate what is the difference of the 3 decibels. Okay, probably we can do this one here. So for example, 1 dB will be equal to, we put into here, then basically that is 20 log 10 of 10. That's called 1 dB. Okay. So log 10 of 10 equal to 1, right? So 1 times 20, and that one equal to 1 dB. That's the definition here. Okay, so from this definition, so probably you can calculate what is the 3 dB. So 3 dB, so therefore 3 dB will be equal to 20 log, will be 3 times of this one, 20 log 10, right? And basically this one is 20 times log 10 of 1,000, right? Because for the log, we can have the formulation, if that exponential, we can take out the multiplication. So basically, the 3 dB in difference that really matters is in terms of the signal, that is the 3 orders of the magnitude in difference. Okay, a little bit, try to get used to it. And the dB is not commonly used in mechanical engineering discipline, but in electrical, they use quite a bit. So, but anyhow, here, if you like, then here we simply take out this one. Okay, so with this one, then we can begin to draw the simple curve here. And again, at this moment, you from this point onward, you have to shift your focus of the thinking into frequency domain. So probably you can borrow the concept of the vibration system that basically is harmonic excitations of using arbitrary the frequency omega. So basically that is the concept we try to move onward forward on this one. So now for this one. So now we can draw the Bode plot, say m of s equal to s over 1. So we can draw the Bode plot of this. We see, okay. So now we can manually develop functions for each, for magnitude, for gain, and for phase. We see what happens here. So here we and j omega equal to j omega here. Then therefore from here we can calculate magnitude. The magnitude j omega will be equal to 1 over omega. Okay. And then here we directly put into dB, so 20 log 10. So here will be 20 log 1 omega. So here we can do further. So the log scale, that's a 1 over, so that is minus 20 log omega. So here sometimes I kind of, not on purpose, I would say sometimes I forgot to write a 10. So by default, if you know that is 10, the log scale at the 10 base, okay. And the phase will be equal to 0, this one. So this one will be constant, minus 90 degrees. Okay, so with those things keep in mind, then we can try. So this one can help us to draw the magnitude. Okay, so here for simplicity, sometimes I kind of drop J. You know what I mean, okay? So for this one, you can see in terms of this is for example, this is just responding. This is y equal to the bx and x equal to this. So basically from here, you can see the slope equal to constant minus 20, right? For this example here. Are you able to see it? Okay, so this is our independent. This is our dependent function. This is our independent variable. So you convert into traditional bx, y equal to bx, this format. Then basically for this drawing is constant. Okay, so here the slope equal to minus 20. Okay, for this linear system. And because here we are not specifying the from where to here, because low scale can be from very negative to, so here we don't specify that this is a region, no. Okay, and then but for kind of the illustration, the magnitude, if you like, you can say when this one equal to 1, then corresponding value of this one will be equal to 20. Then from here, people will know exactly what the curve, how to define this one, okay? And then for phase, so for this one, it's minus 90 degrees. So here is 0 degrees minus 90. So here is constant. Always. Okay, so that's it. Then the next one we can try is a little bit